Welcome to Theory of Computation. This is lecture number 24. We are studying complexity theory, and we are studying two of the most important classes in complexity theory called P, polynomial time, deterministic polynomial time, and NP, non-deterministic polynomial time. Let's have an overview of what these two classes are and why they are so central to complexity theory. The class P is the set of all languages that can be recognized in polynomial time by a deterministic Turing machine. This class is very natural and very intuitive. Polynomial time is what we consider time which is reasonable. If somebody gives us an input of length n, then we can spend order n time on it, or n squared time on it, or n cubed time on it, and claim that we have only spent reasonable amount of time analyzing that input. Thus, P becomes the set of all problems that we can solve in practical or reasonable time. But mathematically, we want to be very precise. We don't want to say this problem is solvable in reasonable time. We want to give a very precise definition of what reasonable time is. And for that, mathematicians and theoretical computer scientists have chosen polynomial time. As I have told you before, the class P is considered by many to be the set of problems that we can solve practically. This definition, of course, has its limitations, as people can argue that if we can solve a problem in order n to the 500 time, then that is not reasonable. However, such cases are extremely rare, and most problems that are of practical interest and fall in the class P, well, we can use our ingenuity and design practical algorithms for it. Virtually all programs that you use are running polynomial time algorithms. If you think of any practical problem that you solve on your computer, such as string matching, it is being solved in polynomial time. In fact, in some cases in linear time, in some cases in quadratic time. When you multiply two matrices, well, the time that you take to multiply two matrices, even if you do it naively, is order n cubed, which is once again polynomial time. Once in a while, we do use algorithms that require super polynomial time or more time than polynomial. However, such cases are extremely rare, and once in a while they give us serious problems. So P is the set of all problems that we can solve practically. That's the intuition behind it. Examples of problems that are in P are, for example, ST connectivity. Given a graph, if you want to know if a given vertex T is reachable from another given vertex S via a directed path, then you can solve this problem in polynomial time by using a version of depth first search or breadth first search. Another problem in P is, for example, given a list, if you want to check if the list is in sorted order. Once again, we can solve this problem in polynomial time. But however, all problems cannot be solved in polynomial time. In fact, we have a long wish list of problems that we would want to solve in polynomial time. So, what complexity theory is trying to do is to identify the boundary between problems which are solvable practically, which are in P, and the ones that are outside P. Of course, it's very easy to think of extremely difficult problems. For example, the halting problem is not in P. We know that from computability theory, our previous part of the course that we did. We know that halting problem is so hard that there is no algorithm that can solve it. However, this is an example of an extremely hard problem, and therefore it is not in the class P, and therefore it's not practically solvable. What complexity theory is trying to do is to identify the boundary. What is it? What is the essential feature of a problem that makes it hard to solve? And just enough hard to solve that it comes out of this class P. The definition of non-determinism becomes very important here. We define non-deterministic Turing machines, and we said that the notion of non-determinism, which is a formal notion, a formal mathematical notion, is roughly equal to the notion of being able to guess something. Non-determinism is equivalent to having the power of guessing. And then we defined NP, the class of all problems that can be solved by non-deterministic Turing machines in non-deterministic polynomial time. You will notice that I'm emphasizing the fact that these problems are solvable in non-deterministic polynomial time. That is because non-deterministic time does not practically correspond to any notion of time that we know of. There is no machine, there is no real device which operates like a non-deterministic Turing machine. You can simulate non-determinism through software. However, that is extremely expensive and requires exponential time. But there is no real machine that you can make which will correspond to a non-deterministic Turing machine. And that is quite intuitive. Roughly, if you think of how a non-deterministic Turing machine operates, it takes an input, and then when it examines the input at any given time, it can make more than one move. So if we were to make such a machine, that machine will have to copy itself all of a sudden, and that is not practically feasible. Nevertheless, non-deterministic polynomial time and non-deterministic time are precise mathematical notions. We defined NP to be the set of all problems that can be solved in non-deterministic polynomial time by non-deterministic Turing machines. The class NP is not really intuitive. In order to get more intuition on this class, what we will do is we will look at certain problems that fall in this class and see why they fall in the class NP. Furthermore, we would also, in today's lecture, find another characterization of the class NP. We will characterize the class NP in terms of verifiers. Since this is a very difficult concept, therefore it would be very useful for us to have an alternative characterization of the class NP. That will allow us to look at the class NP from a different point of view. Since you will have two definitions of the class NP, you will be able to pick the one that you feel more comfortable with and develop more intuition about this class NP. NP is one of the most important classes in complexity theory. It is one of the most widely studied class in complexity theory. Let us look at what is going to be the outline of today's lecture. Today we will revisit the class NP, then we will talk about verifiers and give an alternate characterization of this class NP. We will discuss a few problems that are in NP, namely the Hamiltonian path problem, the clique problem, the subset sum problem. We'll also look at the problem composites, which is in the class NP. So we'll have another characterization of this class. After that, if we have time, we will look at the very famous question called the P versus NP questions. And after that, we will look at the Cook-Levin theorem. We will talk about polynomial time reducibility and head on to the theory of NP completeness. Let us review what we had done in the previous lecture quickly and then go on to study the class NP. Let us recall the class P. P was the union of time n to the k. If we write it more elaborately, it's written as time n union time n squared, union time n cubed, union time n fourth, and so on. Thus, P is the set of all problems that we can either solve in linear time, or we can solve them in quadratic time, or we can solve them in cubic time, or we can solve them in time order n to the 4, and so on. Thus, if we can solve a problem in time order n to the k for some fixed k, we say that this problem is in the class P. Here, I must insist on one thing. Remember that when we say that the problem can be solved in time n to the k, k must be chosen before n. Let me elaborate. What you need to do is to come up with an algorithm which will solve the problem, and for all instances, regardless of how long they are, it would take time order n to the k. You will not be allowed to look at the length of the input and then choose your k. You must choose your k universally for a given problem. So for example, depth first search is a polynomial time algorithm because it runs, say on a computer, it runs in linear time. And this is true for all instances. No matter what instance you give it, it runs in linear time. So that's an algorithm which runs in linear time. Thus, ST connectivity is in the class P. What is nice about the class P is the class P is invariant across various models. We can talk about algorithms, and the class P is the set of all problems that can be solved with polynomial time algorithms. If we wish, we can talk about Turing machines. The class P, once again, is the set of all problems that can be solved in polynomial time by single-tape Turing machines. If we want, we can talk about multi-tape Turing machines. The class P is the set of all languages that are recognized by polynomial time multi-tape Turing machines. Thus, this class is extremely robust, and the definition of this class does not change as you change your models. So, the class P intuitively is the set of all problems that we can solve practically. Now, let's look at the class NP. Remember, we define n time to be the set of all languages that are decided by order n time running non-deterministic Turing machines. NP is the non-deterministic analog of P. So formally, NP is just non-deterministic linear time unioned with non-deterministic quadratic time, unioned with non-deterministic cubic time, and so on. So NP is the set of all problems that can be solved in polynomial time if we had the power of guessing. Non-determinism gives us the power of guessing. Note that the notion of guessing does not correspond to any practical notion. No Turing machine can just guess an answer and always be sure that it is correct. It's just a mathematical construct that allows us to capture something essential about these problems, which are very interesting and very important in complexity theory. Let's start with looking at verifiers now. So now we will look at another notion in computer science, which is called verification. We will talk about special Turing machines or algorithms that we call verifiers. We will try to characterize NP in terms of this new notion called verifiers. Let's first look at the formal definition of what a verifier is, and then intuitively discuss what we want to do with it. Suppose we have a language A. A verifier V for the language A is an algorithm, and remember that algorithm is nothing but a Turing machine. So a verifier is simply an algorithm V such that A is going to be the set of all W such that V accepts W, C for some string C. It is important to note that when we measure the time taken by a verifier V, we measure it in terms of the length of W only. We say that V is a polynomial time verifier if on input W, C, it takes time order length of W to the K for some K. Here, C is called the certificate or the proof of W's membership in A. This definition seems quite daunting, but as we will examine this definition more and more, you will see that the notion of verifiers is very, very intuitive. Let's think about this. You have a language A, and there is a person who wants to be convinced that a string W is an A, but they want to be convinced via some kind of a proof or a certificate. So this person who wants to be convinced of the fact that W is an A is what we call a verifier intuitively. Now, what we have to do is present this person with a correct proof that W is an A. And once we present this person with a correct proof, this person checks the proof very quickly, or checks the certificate very quickly, and accepts that proof or rejects that proof. So basically the verifier is only verifying that C is a correct proof of the fact that W is an A. Well, this notion seems a bit difficult. Let's look at an example. Let's try to understand verifiers more closely by this following simple example. Suppose I wish to become a verifier who verifies that if a given number is composite or not. So what I do is, if you give me a number, I would verify or certify that the number is composite or not. Now, what you have to do is not just give me the number, but a proof that the number is also composite. If your proof is correct, then I will certify that this number n is composite. I will check the proof and certify that the number n is composite. However, if your proof is wrong, I will not certify that the number is composite. Let's look at this example more elaborately. If I am a verifier, what I can do is I can declare that I will accept only proofs or certificates of the form P, Q, where P times Q is equal to n and both P and Q are greater than 1. So what I am doing is I'm declaring that in order for you to convince me that a number n is composite, you have to present to me two numbers which are larger than 1, and if I multiply those numbers, they should give me back n. Of course, any two numbers which are larger than 1 whose product is equal to n is constitute of a bona fide proof that n is a composite number. In fact, this is the very definition of a composite number. A composite number is a number such that we can find two other numbers which are larger than 1 whose product is the given number. Therefore, once I declare that I will accept only these proofs, I become a verifier. Let's look at this example a bit more closely. Now suppose you give me as an input the following pair. You give me 45 along with 5 and 9. The way I will check this proof, so what's your input and the way I'm going to interpret the input is as follows. I will interpret the input as the first part is 45 and you're claiming that 45 is a composite number. The second part, which is 5 with a cross sign and a 9, is a proof you're providing to me that 45 is a composite number. What I have to do is I have to check if this proof is correct or not. How will I check this proof? What I will have to do is to multiply the two numbers that you've given me, 5 and 9, and see if they result in 45. If they do, I will accept this proof. Let's go back to our example. If the input is going to be 45 and 5 cross 9, I will accept this because 5 times 9 is equal to 45. If the input is 45, 15 times 3, I will also accept this pair. I will accept this pair, and because 5 times 9 is 15 times 3 is 45. However, suppose if the input is 45 and the proof is 7 cross 9, I will reject this because 7 times 9 is not 45. So if somebody presents to me 45 and a wrong proof that 45 is a composite, I will reject that proof. So I will reject 45 and 7, 9 because 7 times 9 is not 45. If the input is 45 and 1, 45, once again I will reject this proof because I have demanded that both numbers given to me must be larger than 1. So in this case, what happens is, if you think about the number 45, there are more than one ways of convincing me that 45 is a composite number. One way to convince me is to just say that 5 and 9 are two numbers whose product is 45. Another way to convince me is to say that 15 and 3 are two numbers whose product is 45. So there are at least two ways of convincing me that 45 is a prime. Of course, if you try to convince me that 45 is a prime because 7 and 9 multiplied to give 45, I will reject that proof. So if I'm a verifier of this kind, what I do is I verify compositeness. I verify this language of composites. What that means is that if any number is composite, you can present me a proof that that number is composite and I will accept it. On the other hand, suppose if you have a prime number, you will never be able to find a proof which will convince me that a prime number is composite, because by the very definition of prime numbers, they are numbers which cannot be written as p times q, where p and q are both greater than 1. So for example, if you have the number 13, there is no way for you to convince me or give me a proof that 13 is a composite number. Notice that in the above scheme, if n is a composite number, then there is always at least one way to write it as a product of two numbers that are greater than 1. Thus, for every composite number, there is a proof or a certificate that the number is composite. On the other hand, and this is extremely important, if n is a prime, there is no proof that n is composite. So I will never accept any input of the form n, p, q, where n is a prime. Thus, the language verified by this verifier is exactly composites. What it means is, for every composite, there is at least one way to convince me that the number is composite. In fact, for some composites, there is more than one way to convince me. But what we require is that for every composite, there should be at least one way of convincing me that the number is composite. Secondly, for every prime, there should be no way of convincing me that the number is composite. So you should not be able to take a prime and convince me that the number is composite. And of course, if I am doing my checking this way you will never be able to convince me, say, that 23 is a composite number. So here I was talking not in terms of algorithms, but I was talking in terms of people. You were trying to convince me that a number is composite. Now let us replace me with an algorithm and see if we can write an algorithm which will do the same job as I was doing, and let's analyze how much time it would take. So let's look at the algorithm. Here's the detailed version of it. It takes an input n, and a pair p, q. It checks if p is less than or equal to n, otherwise it rejects. And then it checks if q is less than or equal to n, otherwise it rejects. Then it checks if p and q are both greater than 1, otherwise it rejects. And finally, it checks if p times q is equal to n. If it is not equal to n, it rejects, otherwise it accepts. This is a simple algorithm, and it will only accept pairs n, p, q, where p and q are both greater than 1 and p times q is equal to n. Thus, this algorithm verifies composites. How much time would it take to verify that a number n is composite, given that it's given a correct proof? Well, if you look at this algorithm, the time taken will be proportional to the length of p and the length of q. All we have to do is to take the two numbers p and q and multiply them. And multiplication, if you use the elementary school arithmetic method, can be done in quadratic time. Therefore, this is a polynomial time verification algorithm. So what we have done is we have shown that compositeness can be verified by a polynomial time verification algorithm, or composites are verified by a polynomial time verification algorithm. Let's look at another example. Let's say that we have a directed graph G, and recall what a Hamiltonian path from S to T in a directed graph G is? Well, it is a path that has to start from the vertex S and it has to end at the vertex T. So a Hamiltonian path has to start from S and end at T, since it has to be a path from S to T. The second important thing is that it has to go through every vertex of the graph exactly once. So a Hamiltonian path is a path that starts from a given vertex and ends at a given vertex, and it goes through each vertex of the graph exactly once. If you think about this problem, let's say that you are in a country in which there are lots of destinations, lots of major cities, and you make a graph of this country by putting all the cities as vertices in the graph and connecting two vertices if there is a path, if there is a road connecting one city to another city directly. Suppose you want to start from one source, let's say Karachi, and then go to Lahore, and on your way you want to visit every city, and you want to do that in such a way that you don't go to any city twice, because that would be wasteful. If you can do that in the graph, then we'll say that this graph has a Hamiltonian path from Karachi to Lahore. Let's look at a graph which has a Hamiltonian path. So there is a graph and we have labeled the vertices, and there's a vertex labeled S and there's a vertex labeled T. Now this graph has a Hamiltonian path from S to T. If you look at the path which starts as S, goes to A, then goes to D, and then goes to E, then G, then H, and T, this path visits every vertex exactly once, starts as S, and ends at T. Therefore, this is a Hamiltonian path in this graph from S to T. Well, let's look at the same graph once again, because it has another Hamiltonian path. A graph can have more than one Hamiltonian path from S to T. In this graph, another Hamiltonian path starts from S, goes to A, then goes to G, and then E, and then goes to D, and then H and T. So we have seen an example of a graph which has two Hamiltonian paths. Let's look at another graph. Here is a graph and it has two vertices S and T, and this graph does not have a Hamiltonian path from S to T. To convince yourself that it does not have a Hamiltonian path from the vertex S to T, what you have to do is to stare at this question and try to find one, and exhaustively prove to yourself that there is no way to go from S to T by using exactly each vertex of the graph exactly once. However, this graph is very small, and if you look at it for a little while, you will get convinced that there is no way to go from S to T by using each vertex of the graph exactly once. So we have graphs which do have Hamiltonian paths from S to T, and we have graphs which do not have Hamiltonian paths from S to T. Now, let us make a problem out of it. Remember that all our problems are posed as languages. So, let's look at the following language that we call Ham path. Ham path is going to be the set of all graphs G and pair S and T such that G has a Hamiltonian path from S to T. Right now, we are talking about directed graphs. Thus, every edge has a direction. So, if there is a directed edge from A to B, you can go from the vertex A to the vertex B, but not from B to A, unless you have an edge back from the vertex B to the vertex A. What we want to do is, we want to devise a polynomial time verification algorithm for Hamiltonian paths problem. So, what we want to do is, we want an algorithm, or let's think about convincing someone. Suppose you have a graph in which you know that there is a path, a Hamiltonian path from S to T. Now what you want to do is you want to convince somebody else that this graph has a Hamiltonian path from S to T. Think about how would you convince somebody else that this graph has a Hamiltonian path from S to T. The person that you're trying to convince is a mathematician, and he wants a proof, he wants a certificate which he will check, he or she will check the certificate and say that this graph, they would be able to sure after checking your certificate or proof that the graph has indeed got a Hamiltonian path from the vertex S to the vertex T. In order to verify that a graph has a Hamiltonian path from the vertex S to the vertex T, let's ask ourselves what would be the simplest proof that the graph does have a Hamiltonian path. What will convince you that a given graph has a Hamiltonian path? Let's think about this for a moment. Well, if somebody is claiming that a graph has a Hamiltonian path from S to T, the way I will get convinced is if they show me a path which is a path from S to T and it is an Hamiltonian path. If they show me such a path, then I would get convinced that the graph has a Hamiltonian path from S to T. In fact, that would be a bona fide proof that the graph has a Hamiltonian path from S to T. Now, if we think about it this way, a verification algorithm is very easy to come by. A Hamiltonian path from S to T is a clear proof or a certificate that a graph has a Hamiltonian path from S to T. Now, we can easily design a verification algorithm. This algorithm will take inputs of the form G, S, T and a list of vertices V0 up to Vn. And it will simply check if V0 up to Vn is indeed a Hamiltonian path from S to T. So how will this algorithm work? What would be the format of the input to this algorithm? Well, let's look at this algorithm formally. The input to this algorithm is going to be a graph and two vertices S and T along with a list of vertices. What this algorithm is trying to do is verify that the list of vertices that is given to it is indeed forming a Hamiltonian path. Now, here is the point. If you give me a list of vertices and ask me to check if that list of vertices is indeed forming a Hamiltonian path in the graph, it is extremely easy to check that. Let's look at that, how that is done. All we have to do is to check if the first vertex is equal to S, that the path starts from S. Then we will go and check if the last vertex is equal to T, that the list or the path ends at T. Then we will have to check if all the VIs that appear in this list are distinct and each one of them is a vertex that appears in the graph G. So what we'll have to do is go through this list of vertices which is given to us and make sure that they are all distinct, that none of them is repeated. We can do that easily in polynomial time. All we have to do is match if two vertices are the same. The second thing we will do is we will check if all the vertices of the graph appear in this list and no extraneous vertices appear. So what we will do is simply check if the list V0 all the way up to Vn is a list of all the vertices of the graph without any repetitions. And this can easily be done in polynomial time. Once we have done that, what we want to do is now we know that this list starts with the vertex S, it ends with the vertex T, it has all the vertices of the graph exactly once. So all we have to do is to check if it's a Hamiltonian path. How will we check if it is a Hamiltonian path? We start from the first vertex and make sure that there is an edge from V0 to V1. Then we make sure that there is an edge in the graph from V1 to V2. Then we make sure that there is an edge from the graph V2 to V3 and so on. So the next step is very simple. We just simply run a loop for n-1 times and check if all those edges are present in the graph. If we analyze the time taken by this algorithm, we realize that it runs in polynomial time in the number of vertices in the graph, and therefore it's a polynomial time verification algorithm. Why is it a verification algorithm? Well, let's argue that once again. Suppose a graph has a Hamiltonian path from S to T. Then there is at least one way for somebody to convince this algorithm that the graph has a Hamiltonian path from S to T. That is, if they give it the correct list, which forms a Hamiltonian path from S to T, this algorithm will accept. On the other hand, if there is a graph which contains no Hamiltonian path from the vertex S to the vertex T, then no matter what list you give it, this algorithm will reject. So this algorithm will never accept a graph along with the proof. Any graph which doesn't have a Hamiltonian cycle, all proofs that you try to give it, the algorithm will reject. And therefore, this algorithm verifies, or it's a verification algorithm for the Hamiltonian path problem. Let's think about what we have done. What we have done is come up with a polynomial time verification algorithm, an algorithm that verifies if a graph has a Hamiltonian path or not. Note that we must provide this Hamiltonian path to the algorithm as an input. How we find this Hamiltonian path is not addressed in a verification algorithm at all. In fact, it is not the algorithm's verifier's responsibility to find a proof. The verifier's responsibility is only to check the correctness of the proof. Thus, problems that can be for which we have verification algorithms, polynomial time verification algorithms, always saying is that there are proofs of memberships which can be checked in polynomial time. We are not addressing the issue of how hard would it be to find such a proof. Let's look at this thing a bit more closely. What we have done now is we have come up with a polynomial time verifiable proofs of membership of composites and also for Hamiltonian paths. We have shown that composites and Hamiltonian path are both problems that have polynomial time verification algorithms. Note that it may be very, very hard to find these proofs, but once such proofs are found, they are very easy to verify. So I have constructed an example for you. What I want to do is I want to convince you that some number, some given number is a composite number. So let's look at this number on the screen and see what this number is. The number is 416681. What I want to do is I want to convince you that this number is composite without overburdening you, without asking you to do a lot of work. One way for me to convince you that this number is composite is to give this problem to you as a homework. I can ask you to go home and try to factor this number. If you try to factor this number, you will realize that you will have to spend a lot of time in just factoring this number. This number is not very easy to factor. But what I did was I went and factorized this number somehow, and now I'm just trying to convince you that this number is a composite. So I present to you the following proof that 416681 is a composite. I simply claim that 416681 is equal to 2377 multiplied by 1735. So the pair 2377, 1735 is a proof that this number is composite. Of course, you cannot be convinced that this proof is correct unless you multiply these two numbers. However, these are 2 4 5-digit numbers, and you can multiply these two numbers in probably less than 2 minutes. And if you do that, you will realize that the answer is correct. Answer is what I claim. It is 416681. Thus, when you multiply these two numbers, you will get the answer back. So this is a bona fide proof that 4166 and so on, the number that I just said, is composite. Now, how did I find these two factors? Let me tell you one more thing. these two numbers that are factors of these numbers are themselves primes. They're reasonably large primes. So I must have had to do a lot of work in order to find these two factors. But once I found them, it's very easy for me to convince you that this number is composite. So what is important here is that verification is easy. Multiplying numbers is easy, and therefore if you multiply these two numbers, you can easily verify that this number is composite. I am not saying how hard or how difficult it is to actually find the proof that this number is composite or any number is composite. I'm simply saying that these proofs are easily verifiable. For you to understand this point, for example, let me give you another number. Let's try to find a proof that 1386249 is composite. If you go home and try to find a proof this number is composite, you will have to do a lot of work. So your homework today is to try to find a proof that this number is composite. So you have to factor this number and verify the previous number that I have given to you as a composite number. When you do that, you will notice that verification is very easy. It's simply a multiplication with few digits, which you can do by hand very easily. On the other hand, if you try to find a proof that this number is composite, well, it would take you some time. In fact, no one has come up with a polynomial time algorithm which can factor a number. So finding prime factors of numbers is a difficult problem which has not been solved. Similarly, it may be very difficult to find a Hamiltonian path from a given vertex to another given vertex in a graph. But once a path has been found, it can be easily checked that it's indeed a Hamiltonian path in the graph. What we are doing now is designing verification algorithms. Remember that when we design verification algorithms, these algorithms don't actually solve the problem in question. They only provide us a way of verifying that a given solution is indeed correct, or a given proof or a certificate is indeed correct. Let's look at one more problem in order to get a feel for this idea. Let's recall what a clique in a graph is. A clique in a graph is a set C of nodes that are all connected to each other. More formally, we say that C is a clique in a graph if for every vertex x and y in C, where x is not equal to y, x and y are connected with an edge. The clique number of a graph is the size of the largest clique in G. Now let us consider the following question, which is what we call clique. This is a language. It consists of pairs G, K such that G has clique number at least K. So given a graph G, a clique in a graph is just a set of vertices such that all of them are connected to each other. And the clique number of a graph is the size of the largest such set. So if I tell you that a graph has clique number 12, what that means is that there are 12 vertices in the graph that are all connected to each other. If I say the clique number of a graph is at least 15, then there must be at least 15 vertices in the graph such that they are all connected with each other. Let's look at an example. Here we've shown you a graph G0 with clique size 6. Let us note that if I take the vertices A, X, C, F, D and Y, that is a clique in the graph. That is a complete graph or a complete subgraph in this graph. These are 6 vertices that are all connected to each other. Therefore, the clique number of this graph is at least 6. If you stare at this graph for a little while, you will convince yourself that this graph does not have a clique of size 7. There are no 7 vertices which are all connected to each other. So the clique number of this graph is exactly 6. Hence, if we look at the pair G0, 6, that would be in the language clique, and if we look at the pair G0, 7, it will not be in the language clique. So Intuitively, you can think of the following question. You're given a graph G and a K, and you're asked if the clique number of the graph is greater than or equal to K or not. If it is, you will accept the input. If it is not, you will reject the input. That would be solving this problem. Now what we want to do is we want to come up with a verification algorithm for the clique problem. So what does it take for us to come up with a verification algorithm for the clique problem? Well, we will devise a polynomial time verification algorithm for clique. Let us consider the problem first. We have to verify if a given graph has a clique number greater than or equal to K. What would be the simplest proof of the fact that a graph has clique number at least K? What would convince you that a graph has a clique number at least K? Let's think about this for a moment. Well, what will convince me that a graph has clique number K is if you show me K vertices in the graph which form a clique. That would be the most convincing proof for me, the most convincing certificate for me that would show me that a graph has clique number at least K. A clique of size K itself is a clear proof or a certificate that a graph has clique number at least K. Now a verification algorithm for this problem is easy to design. The algorithm will accept inputs of the form G, K along with a list of K vertices. And this algorithm will simply check if the list of vertices is indeed a clique in G. Checking if a list of vertices is indeed a clique in a given graph is not hard. It can be easily done in polynomial time. Let's look at the details. This algorithm on input G, K and a list of M vertices will first check if M is at least K. Then it will check if all the vertices in the list are distinct. Once again, this can be done in polynomial time. And then it will check if all the pairs of vertices are connected by an edge of G. So we will run two loops. One loop will go from 1 to M and the other loop will go from I plus 1 to M, and we will check if the edge Vi, Vj is indeed an edge in the graph. If we perform these checks, then we actually verify that the given list is a clique in G. And since we also checked if the list has size at least K, we will be convinced that this graph has indeed clique number at least K. It's very easy to see that this is a polynomial time verification algorithm for the clique problem. So what we have looked at now are three problems: Hamiltonian path, the composites, and clique. And what we have seen is that for these problems we can easily find polynomial time verification algorithms. Let's look at one more problem which is slightly different from the ones that we have seen. The first problem had to do with factoring and numbers. The other two problems were from graph theory. This is a slightly different problem. It's called the subset sum problem. Let's consider a set of numbers. So for concreteness, I have taken the example of the set 1, 3, and 6. So this set has 3 numbers in it, integers in it. If we think about how many subsets it has 2 to the 3 subsets. What we can do is now look at each subset and add up the elements that occur in that subset, and that is called a subset sum. So, for example, for this particular set 1, 3, it has 8 subsets, so we get 8 subset sums. Let's look at them. Well, the empty set gives us the sum 0, the singleton set 1 gives us the sum 1, 3 gives us the sum 3, the singleton set 6 gives us the sum 6, the set 1, 3 gives us the sum 4, since 1 plus 3 is equal to 4. The set 1, 6 gives us the sum 7. The set 3, 6 gives us the sum 9. And the whole set itself sums up to 10. Note that there is no subset of this set that sums to 5. So we are given a set and we can enumerate all the subsets of it, and we can sum them up and they give us different numbers, and those numbers are called subset sums. Now let's define the subset sum problem. In the subset sum problem, we are given a set and a target number t. and we are asked if there is a subset of S whose elements sum to T. So formally, the subset sum problem consists of pairs S comma T such that there exists a capital T which is a subset of S which sums to exactly little t. Note that given a set S, it has 2 to the n potential subsets. And if we start enumerating all those subsets and summing them, that would take us exponential time. What we want to do is, we want to show that for the subset sum, we have a polynomial time verification algorithm. So think about it. What would be the best way to convince you that a given set S has a subset that sums to T? If we want to devise a polynomial time verification algorithm for the subset sum problem, we have to think of a proof which would convince us that some subset of S sums up to T. Well, if I think about it, the easiest proof of the fact that some subset of S sums up to T would be the subset T itself. If you provide me T, then I can add it up and see if it adds up to T. Thus, a verification algorithm will take S, T, and capital T, and all it has to do is to check that capital T is indeed a subset of S, and then add up the elements in T and see if we get little t. This would be a polynomial time verification algorithm for the subset sum problem. Well, we've run out of time today, so we will leave this algorithm at this point. You can go home and think about this algorithm. In the next lecture, what we would do is we'll go through this verification algorithm once again, and then we will argue that problems which have polynomial time verification algorithms are exactly the problems that belong to the class NP. And this way we will get an alternate characterization of the class NP. Then we will start looking at the P versus NP question and the theory of NP completeness. Thank you. I'll see you next time. Goodbye.